Hello everyone, my name is Huang Yingting. Today our group is going to introduce a revolutionary technology in the field of wastewater treatment, membrane aeration biofilm reactor, which comes from Fluence Corporation in the United States. This technology has attracted much attention in the field of environmental engineering in the recent years because of its high efficiency and low energy consumption. According to a report by the United Nations Environmental Programme, about 80% of global sewage is discharged directly and untreated, leading to serious water pollution and ecological damage. In developing countries, the coverage of sewage treatment facilities is less than 30%, and many cities and rural areas lack basic sewage treatment capacity. The traditional biofilm method has the following main limitations. Firstly, it relies on the high energy consumption of the external aeration system for oxygen supply, with low energy efficiency. Secondly, the system is sensitive to the fluctuation of water quality and is prone to biofilm detachment. To solve the limitations of traditional wastewater treatment technology, MABR technology has emerged. This picture is a diagram of the MABR. It has advantages over traditional technologies, including energy efficiency, small footprint, etc. This technology can be adapted to any size at any need for wastewater treatment.
This part presents the core mechanisms of MABR. The MABR is a spiral self-repairing membrane that supports the formation of aerobal films in an anostic environment, resulting in simultaneous nitrification and denitrification. When semi-permeable membrane is submerged into the tank, low pressure air is brought through the air sides. Oxygen is constantly supplied to the fixed nitrified biofilm that develops on the water side, while denitrification occurs in the anaerobic layer. The low-pressure passive aeration offers significant energy savings over a conventional high-pressure aeration. During the working process, a three-layer structure biofilm spontaneously forms on the membrane, enabling simultaneous nitrification and denitrification. These layers are identified as the aerobic layer, anaerobic layer, and anoxic layer, respectively. The aerobic layer is located close to the membrane and exhibits a high oxygen concentrations. The main bacterial community within this layer consists of nitrified bacteria. Nitrification in this region occurs in two primary stages. First, oxygen diffuses through the membrane into the water, where it reacts with dissolved amino acids under the influence of ammonium oxidizing bacteria to form nitrite. Second, nitrite oxidizing bacteria further change the nitrite into nitrate. The anaerobic layer is near the water side and maintains an oxygen concentration close to zero. This layer primarily harbors denitrifying bacteria, which unitize dissolved organic carbon sources in the water to progressively reduce nitrate into harmless nitrogen gas and water. Furthermore, some denitrification reactions also occur in the anostic layer, which lies between the two parts. This mechanism allows MABR to achieve the denitrification process traditionally require multiple reactants on a single membrane, thereby significantly simplify the treatment process and enhancing efficiency.
Now I will introduce the process of membrane-aerated biofilm reactor system. The MABR process works in 5 main stages. The first is effluent and pre-treatment. Wastewater enters the system through the sealed field tank, where it's pumped to the treatment unit. The circulation pump ensures stable hydraulic conditions for effective treatment. Then it is the cold treatment unit, which has been informed in the former part. At the same time, the nitrogen and the CO2 are expelled through the exhaust system, and the treated water exits the system as clean liquid. Also, real-time conditions are mentioned by pH and dissolved oxygen probes. Pressure gauges and throttle valves help regulate oxygen pressure and water flow, while sampling ports measure key parameters like COD and ammonia nitrogen. Outside the core unit, the transparent casing allows for easy observation of biofilm growth, and the concentric solid core reinforces the membrane, ensuring long-term stability. This table compares three different systems, MABR, MBR, and RO, on key aspects. For the core process, MABR integrates nitrification and COD removal in a single tank, while MBR needs multiple tanks. As for oxygen supply, MABR uses membrane-based oxygen transfer, more energy efficient than MBR's bubble aeration. Also, MABR handles both nitrogen and COD removal together, unlike MBR, which requires extra equipment for nitrogen. What's more, MABR is 50% more energy efficient than MBR, reducing aeration energy consumption. In summary, MABR is simpler, more energy efficient, and requires less space compared to MBR.
Moving on, how do we establish this crucial biofilm? It's not like the fermentation process used in industry. We call this process biofilm startup, cultivation, or acclimation. We mainly use the natural microorganisms already found in the wastewater. These microbes gradually attach to the new membrane surface, grow, and produce a protective slime layer. Over time, the biofilm matures and divides into different zones we talked about, where there is or isn't oxygen. This process isn't instant. The speed of the process depends a lot on the temperature. Warmer conditions speed it up, while colder ones slow it down a lot. It usually takes a few weeks to months to grow a fully working and stable MABR biofilm that is ready to be used effectively. Finally, after the MABR module has biologically treated the wastewater, we need to make sure the final water is clear. This requires a step where the water is separated. The most important thing we need to get rid of is sloughed biomass. Basically, bits of the biofilm that naturally come off over time, along with any other bits in the water that have not been filtered out. The most common and standard method is gravity settling, using a clarifier or sedimentation tank. The heavier parts of the plant sink to the bottom, leaving clean water on top. For situations where the water needs to be really clean, maybe for water reuse, a better option is membrane filtration, like microfiltration or ultrafiltration. These create what's called an MABR-MBR configuration, providing a near-perfect physical barrier to solids.
I'll demonstrate how Bloom's MABR technology doubles the treatment capacity at my wastewater plant without physical expansion. The plant faces severe overloads. Effluent COD at 935 mg per liter and the TSS at 645 mg per liter, exceeding design by 50%, with strict reuse requirements. Conventional solutions were inadequate. The Super MABR retrofit provided the answer through three key advantages: space efficiency, Modulars integrated into existing infrastructure. Energy saving, 33% reduction in aeration energy and process efficiency. Single-pass treatment without recirculation. The results were exceptional. TSS reduced to 2 mg per liter, COD lowered to 24 mg per liter, and daily TSS loading reached 11,378 pounds, 48% above design capacity, all while consistently meeting agricultural reuse standards. This case study demonstrates MABR's potential to address critical wastewater challenges, accommodating population growth within existing footprints, reducing operational costs through energy efficiency, and achieving sustainability goals without chemical additives. MABR represents a paradigm shift, delivering superior performance with reduced resource requirements. The evidence is clear. MABR isn't just an upgrade, it's a paradigm shift. At MCEE, we saw how this technology turned crises into triumphs, breaking every performance barrier without expanding the plant. But this is bigger than one facility. In a world where 80% of wastewater flows untreated, energy costs are soaring, and the space is at a premium. MABR delivers what no other technology can: maximum treatment, minimum footprint, and future-proof flexibility. Where you are retrofitting aging plants or building a new, MABR is the key to sustainable wastewater management. The question isn't, can you afford to upgrade? It's, can you afford not to? Let's build this cleaner future together. Thank you.